Welcome to lecture 71 on essentials of topology. We have already studied the notion of compactification in lectures 59 and 60, namely one-point compactification. In this lecture, we will study the notion of compactification called Stone-Cech compactification. Begin with what we have already studied, that if we are having a real line with Euclidean topology, we know that if we are taking this semi-open interval, that is 0 to 1, this is not a compact subset of R, but at the same time this semi-open interval is contained in this closed interval 0 1, that is compact. It means that there exists a compact set containing this semi-open interval 0 1, which is not compact. Specifically, what we have seen that this closed interval 0 1 is precisely one point compactification of this semi-open interval 0 1. Question is it only the compact set containing this semi-open interval? Answer is no. We can construct a number of compact sets containing this semi-open interval 0 1. So let us take this is 0 1. We can construct another closed interval. Let us take this one, which is compact and that is also containing this semi-open interval. Even we can talk about much more. So the question is, when we are discussing about this Stone-Cech compactification, how this concept is going to differ from the concept of one point compactification? Answer is, actually whenever we are talking about this one point compactification, this is in some sense the minimal compactification, while when we are talking about this Stone-Cech compactification, this one is the maximal. Moving ahead, and let us see the concept of compactification first. So what compactification of a topological space means? A compactification of a topological space x tau. This is a compact Hausdorff space. Let us take that is y tau dash with x tau as a subspace of it, that is this is a subspace of this y tau dash, satisfying the restriction that closure of x is equal to y. And in case if there are more than one compactifications, can we say that these compactifications are equivalent? Answer is yes, and that is given here. If we are having two compactifications y1 tau 1 and y2 tau 2 of a topological space x tau, then we say that these two compactifications are equivalent if there is a homeomorphism in between these two, that is a homeomorphism H from the space y1 tau 1 to y2 tau 2 such that Hx is equal to x for all x in X. Now question is, if we are beginning with a topological space x tau and this has a compactification, can we fix the nature of this space, or is there any well-known space in topology? Answer is yes, and that are known as completely regular spaces. So before justifying that if a topological space has a compactification, then it will always be completely regular. Let us see what this concept is. We have already studied the concept of T4 spaces as well as normal spaces. Let us have a look on that. We say that a topological space x tau is T4 if each pair of disjoint closed sets A and B, there exist open sets G and H such that G is containing A, H is containing B, and G as well as H are disjoint. We have also seen that a normal space is nothing but a space which is T1 as well as T4. Further, we have seen that instead of open sets for separation of disjoint closed sets, it can be achieved by using the concept of continuous function, and that is the well-known Eurozone lemma. This lemma states that if we are having a normal space x tau and if we are having a pair of disjoint closed subsets A and B of X, then there exists a continuous function f from this x to closed interval 0 1 such that fx equal to 0 for all x in A and fx is equal to 1 for all x in B. Before studying the concept of normal spaces, we have also studied the concept of regular spaces, and what we say that a topological space x tau is regular if it is both T1 as well as T3. What concept of T3 we have studied? We have studied that a topological space x tau is T3 if every pair consisting of a point and a closed set, that is f subset of x which is not containing this point x, there exist open sets G and H such that x belongs to G, f is a subset of H, and G intersection H is an empty set. The idea is that here we are discussing the separation of a point from a closed set by using open sets. A natural question comes. Similar to the case of normal spaces, what we have seen by Eurozone lemma that separation can be made by using the concept of continuous functions. So, question is, can we separate a closed set from a point by using the concept of a continuous function? Answer is not in terms of regular spaces, and that is precisely given in terms of completely regular spaces. Now let us see the concept of completely regular spaces. Similar to the concept of regular spaces and normal spaces, a topological space x tau is completely regular if it is both T1 plus an additional thing, that is T3 and half space. And what is it? We say that a topological space x tau is T3 and half if for every pair consisting of a point x and a closed set f subset of x with x is not an element of f, there exists a continuous function f from x to closed interval 0 1 such that f of this closed set f is singleton set 0, that is image of closed set under this function f is the singleton set 0, and this function send this x to 1. And as stated earlier that a completely regular space means that this is t1 plus t3 and half. Now, what we can conclude here that every normal space is a completely regular space. So, normal spaces are completely regular. Question is, how is it possible? Answer is, use Eurozone lemma. And the fact that if we are taking f subset of x, this is closed. Also, let us take x which is not in f. Note that this singleton set x is closed. Why? Because this space is a T1 space. Also, what we can justify that completely regular spaces are regular too? Question is, how is it possible? Answer is, if we are taking a completely regular space, this is t1 plus t3 and half. And now let us take the definition of this t3 and half. What we say that if we are taking a closed set and an element x which is not in f, there exists a continuous function f from this x to closed interval 0 1 satisfying these two criteria. So if we are taking a set G which is defined as inverse of this semi-open interval, now what we can say that this G always contain F. Also let us take a set H which is F inverse. This is half and this is 1. So this is semi-open interval closed at 1. Note that this will always contain X. From the construction itself, it is clear that G and H are disjoint. Also, these are two open subsets of X. Why? Because F is continuous and the second fact is that this semi-open interval 0 half and if we are taking this semi-open interval half to 1, both are open subset of these are open subsets of this closed interval 0 1. Thus we say that every completely regular space is a regular space. Now let us see a simple result about a completely regular space which we have to use. So what this result is that a subspace of a completely regular space is completely regular. In order to justify this result, let us take a completely regular space x tau. So what we are taking that this space is completely regular. Now let us take a subset y of x and our interest is to show that this is also completely regular. So this is given to us and this we have to justify. It is to be noted that if this space is T1 then this will always be a T1 space. So what exactly we have to justify that if this space is T3 and half, then try to justify that this space is also satisfying the requirement of T3 and half. So how to justify it? Now let us take a subset f of y. Note that this f is closed and take an element y which is not in this f. Note that when we are saying that this is closed, meaning is that this is tau y closed. Also what we know that if we are finding out this closure of f in y, this is nothing but y intersection closure of f in x. Also as we are saying that this f is tau y closed, so this will be precisely f and this is equal to y intersection closure of f. Note that this closure of f is closure of this set f but with respect to topology tau. Now what we have with us, this closure of f is a subset of x. It is to be noted that this is closed. Also it is to be noted that y is not an element of closure of f. Now because this space is completely regular and satisfying the criteria of T 3.5 spaces. So what we can say that there exists a continuous function. Let us take that function as f from this space x to closed interval 0 1 such that what we can say that the image of this closed set under F is singleton set 0 and image of this Y is precisely 1. Now let us take the restriction of this function on Y. So obviously this is from Y to 0 1. It is to be noted that this function will always be continuous. Also, if we are computing the image of F under it, that will be precisely singleton set 0, and also if we are computing image of Y under this function, that will be 1, and thus this space Y tau Y is 3.5, and therefore this space is completely regular. Having this idea of completely regular spaces in mind, let us move to the concept of compactification again, and this is one of the example of or one of the use of compactification. What we can show that if any topological space is having a compactification, that space will always be completely regular. In order to justify it, let us take a topological space x tau and let us take this space y tau dash. This is compactification of topological space x tau. Now if this is compactification, what we can say that this space y tau dash is compact Hausdorff space. Note that what we have already studied, that every compact Hausdorff space is normal. So this one is normal. Also what we have studied, that every normal space is completely regular. So this y tau dash is completely regular, and at the same time this x tau, this is subspace. What we have studied, that subspaces of a completely regular space is completely regular, and therefore this is also completely regular, and that's the justification of this statement, that if x tau has a compactification, then x tau will always be completely regular. Question is, what about the converse of this statement, that whether every completely regular space has a compactification? Answer is yes, and that we can see. But before proving this statement, let us prove a lemma, and that lemma uses a concept, that is the concept of embedding. We have already studied the concept of homeomorphism. So from there we can see that what the concept of embedding is. So actually an embedding, or this is also known as topological embedding of a topological space, let us take it as x tau into, in the topological space, let us take that space as y tau dash. This is precisely a function f from x to y, which maps or which sends x homeomorphically. So this is morphically onto the subspace Fx with relative topology on it, and this is subspace of Y tau dash. With this concept of embedding, let us see this lemma. What this lemma states that for topological spaces X tau, and let us take Z with topology tau dash on it, where this space is a compact Hausdorff space, and also let us take an embedding from topological space X tau to this topological space Z tau double dash. Note that again this is a compact Hausdorff space. Then there exists a compactification Y tau dash of the topological space X tau, and this has the property that there is an embedding. Let us denote this embedding by capital H. This is corresponding to this one from topological space Y tau dash, which is a compactification of this space X tau, to the given compact Hausdorff space Z tau double dash, and the property of H is that it equals this small s on X. And further, the compactification Y tau dash about which we are discussing is uniquely determined up to equivalence. So let us prove one by one. Before proving this lemma, let us use this terminology that this space Y tau dash, this is called compactification induced by embedding H. Now let us see the proof of this lemma. Begin with what we have in our hand, that this is an embedding. So here this is an embedding H from this topological space X tau to the topological space Z tau double dash. Now as it is a function, this will send this X to Hx. Note that Hx is a subset of Z. What we can do here, why not let us take this Hx as a new set, that is x naught, and further let us take the closure of this x naught as y naught. So what we have in our hand, that this y naught is a subset of Z. Even we can talk about the relative topology on this y naught, and we can say that this is a subspace of this topological space. What this topological space is, it is to be noted that this is compact Hausdorff space. Obviously, we can say that this is Hausdorff. Further, because this y naught is nothing but closure of x naught, this is a closed, and this is a closed subset of a Hausdorff space. So we can also say that this space is compact too. Thus, this is a space which is compact Hausdorff. And what about closure of x naught, that is y naught? So from here, what we can say that this y naught with this relative topology on it, that is this tau double dash y naught, is a compactification of x naught with relative topology on it. Now our motive is to construct this set Y. Question is how to construct it. Idea is, in order to construct this y or to find out a new topological space y tau dash, but we are going to justify that this pair, this xy, is homeomorphic to this pair of spaces, that is x naught, y naught. In order to justify that this pair is homeomorphic to this one, let us take a set. So we are taking a non-empty set A, and how this is going to be help us, we will see it. But what are the features of this A? The first one is that this is disjoint from X, and the second one is that this A is in the bijective correspondence with this difference, that is y naught minus of x naught. It means that there exists a bijective function. Now let us take, or let us denote that bijective function by k from this A to this set, that is y naught minus x naught. Now let us define this y as the union of x with A. Further, let us define a bijective function. This we are denoting by h from y to y naught, and this function is defined as h of y. This is equal to small h of y if y is in x, and this is ky if y is in A. Also, let us define a topology, that is this topology tau dash on this y edge, that we say that any G is a member of this topology tau dash if and only if this H of G is an open subset of y naught. Now from here, the one thing is clear, that this H is a homeomorphism. As this map is bijective, and we can see that how this is defined in terms of H as well as K. Also, the second thing is that this x tau, this is a subspace of this topological space, that is y tau dash, and why this is because what we can say that this restriction of h over x, that is nothing but this small h. Thus what we have in our hand, that this h from this y to y naught is a homeomorphism, and now if we are expanding it, so what we can conclude, that h from this y with topology tau dash to this space z, this is an embedding. That's the proof of the first part. In order to prove the second one, let us take two spaces. Why not let us take y1 tau 1 instead of this yn tau dash, and let us take another space, that is y2 tau 2. What we are saying, that these two are compactifications of this topological space X top. Now let us define two maps. H1 is from this Y1 to Z and H2 this is from Y to Z. We are not mentioning here topology. These are embedding and at the same time these are extension of H. Now if we are taking this I which is 1 2, if we are looking for what HIX is, that is nothing but this is small hx, that is precisely x naught. Question is, can be justified from here that this for I is equal to 1 and 2, if we are looking the image of y under hi, that is precisely x naught bar. Answer is yes, and we can justify it. Question is how, and this is or this follows from the fact that this hi is continuous. It is to be noted that this x naught is contained in hiy. Question is whether this hiy is closed. Answer is yes. Why? Because it is compact. Why it is compact? Because this is continuous image of a compact space and compact subspaces of a Hausdorff space are closed. Therefore, this HIY is a closed set. Now, using the concept of closure, what we can deduce that this HIY will always be equal to x naught closure for I is equal to 1 and 2. Now, if with these functions h1 and h2, what we can deduce that if we are having this topological space y1 tau 1, this is z tau double dash and this is y2 tau 2. Note that this is a function h1 and this will be precisely inverse of h2 and their composition will be h2 inverse composition h1 and how this will behave on elements of x. So if we are taking any x in x and we are trying to find out h2 inverse composition h1 on this x, note that this is precisely x, that is this is identity on x, and that's all to justify that this compactification y tau dash is uniquely determined up to equivalence. And thus what we can conclude that the compactification is uniquely determined up to equivalence. That's the proof of this lemma. In the next lecture, we will see that every completely regular space has a compactification. These are the references. That's all from this lecture. Thank you.